Welcome everybody. Thanks to everybody who's contributing today and everybody who's come along with an interest in probabilistic programming for infectious disease modelling. This day is part of a month-long program on modelling and inference methods for pandemic preparedness. It's a program which is being run and populated by lots of infectious disease modelers who took part in various countries' responses during the COVID pandemic. And really we're asking questions over where do we go next with our research and what are the gaps that even after COVID remain unfilled for a lot of our kind of methods and our work. So we thought that a day on probabilistic programming would be a good idea to try and really cross some boundaries and reach out, get the epidemic modelling community to reach out more to the computer scientists and actually start talking particularly about what kind of domain-specific languages probabilistic programming concepts can offer to the disease modelling community in terms of making their work more robust, more flexible, more agile, more responsive, particularly for a future pandemic. Just a very quick word from one of our sponsors who's buying you lunch today. Mars Mathematics for AI in Real-World Systems is a new £15 million investment that we're running at Lancaster. And really it's kind of to launch a research program between applied mathematics, so dynamical modelling, infectious disease modelling is dynamical in the most part, and kind of modern techniques in AI research. And we're hiring 10 new academics, research fellows. We've got some software engineering going on. And then we have 4 kind of application streams in cybersecurity, environmental science, engineering, and the one that I'm attached to, which is health. So if you're interested, then please do talk to any of the Lancaster people here more. We'd love to tell you more about it. So what are we aiming to do today? What's the order of the day? Well, what I wanted to do is really try and connect epidemiologists and modelers with mathematicians and statisticians here in the audience, with computer scientists as well, because I think traditionally, particularly computer science has been probably the weakest of the 3 pillars of our subject, and I think it's high time we try to strengthen that link. As I previously said, what we'd like to do really is to explore DSLs and probabilistic programming as a way to improve the transparency of our subject. Can we abstract models away from the logic of actually implementing them? And the idea is to improve reproducibility so that we can swap models between modelers, we can compare and contrast. We can improve the performance of our models because often modelers need to produce results kind of overnight or on a timely basis. So if you have something like COVID, running your model for 3 months on an HPC is not really an option. We need results tomorrow morning. We want some way to manage complexity because as we get our hands on more data streams coming from places like UKHSA, the national health agencies, crowdsourced data from telecoms companies, we need to manage that data in a way that fits into our model, but in a way that we can still have a kind of transparent model structure. And ultimately, we want to increase trust in our science. So that's trust between ourselves in the scientific community that each other's code is in some sense correct, but also increase trust with policymakers so that they know our models have been soak tested properly. We've explored a range of model structures, perhaps bringing those different model structures together in ensemble predictions. And then finally, to increase public trust in model-based policy advice. So here's a quick rundown of the talks for today. I'm going to stop gassing in a little bit, and we might have lots of time to kind of network. But basically, we kick off in about 25 minutes, and then we've got a morning break and some more talks, and then lunch, as I said, for a good hour, and then we'll just go through the day and into a discussion, panel discussion, by about 3:30. And really, the end of the day is quite flexible. And if anybody's up for taking the discussion into town later, then you're all very welcome. Okay. So I thought I'd sort of start off by introducing infectious disease models as best I can in 5 or 10 minutes. What are infectious disease models? Well, they're a subset of a much wider class of state transition models, sometimes called state space models. And really, they're characterized by thinking about the population as existing in a number of kind of mutually exclusive states. It's pretty much what we all do. So my example model here on the right thinks about an individual who sort of notionally starts off as susceptible to disease, and then at some point might become infected, and once they're infected, then they might recover from the disease, or if they're unlucky, they might even die from the disease. And on the way, they might actually get vaccinated. So you've kind of got this competition between, who gets you first, the nurse with a vaccination needle, or the disease that, hopefully you're trying to avoid. And if you are vaccinated, then, hopefully you don't get the disease, but as we've all learned from COVID, vaccines aren't perfect. You might actually still get the disease, even though you're vaccinated. And so models such as this can tell us quite a lot about, firstly, the efficacy of something like a vaccine program. We can also think about, what is it that characterizes the rate at which we go from being susceptible to being infected? And the thing that makes epidemic models mathematically interesting is that the rate at which you undergo that transition is related to who around you in the population is currently infected and is kind of sort of raining virus particles down on you. And we like to kind of unpick particularly this infection rate and write down this kind of transition rate in terms of observable covariates, such as the presence of a contact network, or maybe a spatial effect, or the effect of your age class, or where you go to school, or where you go to work. And lots of the interesting policy information can be drawn out of actually taking these models and fitting them to case data and trying to estimate parameters that govern what those transition rates actually turn out to be. So we characterize populations by state. There's also a kind of an aspect of stratification in these models. We might want to stratify the population classically by age classes, but it could be by deprivation index, it could be where you live, which local authority you live in, for example. And so from these models, you get a continuum from what the physicists would call a mean field model, where we kind of assume that everybody just kind of mixes homogeneously in the population, right the way through to an individual-based model or an agent-based model, where we're actually representing individuals within our model at the finest granular level. So we can specify a model by states, by stratifications, and by transitions, the edges in this state transition graph. But then we kind of need to evolve this state through time. And certainly in the epidemic modeling literature, there are kind of three main ways of doing this. One is to write the model down as a set of ordinary differential equations. And you might well do this if you're a physicist used to kind of doing fluid dynamics or modeling sort of gas flows and all that kind of stuff, where each ODE, each differential equation, kind of looks at the rate of change of the number of individuals in each of these kind of compartments. And those models are really useful for kind of thumbological advice during a pandemic. You can kind of explore the likely effect of, for example, vaccinating a proportion of the population. You can do maths on deterministic equations, and you can come up with kind of thresholds that suggest things like vaccination strategies and kind of strategies for managing the epidemic in various different ways. But I think a lot of us have gravitated towards stochastic or kind of random setups for these models, reflecting the fact that, you know, if I cough now, it's not a foregone conclusion that the people close to me are going to get infected with an infectious disease. Okay, it's a probabilistic, it's a chance event. So we can set these models up, and we can do it in two different ways. The kind of first way of doing it is to model these things as continuous in time. So events happen at time points, and those events really are transitions of an individual along edges in our state transition graph. So they can happen in continuous time, and there are a few algorithms, the Doob-Gillespie algorithm, that we might use to set up those models. We might also take an Euler discretization of time and actually evolve our state in discrete time steps. And there are advantages of doing that for kind of dealing with large populations. Definitely advantages of doing that on a computer. Computers are kind of discrete beasts, and I think most people who write these models might agree that actually kind of doing computation in discrete time is probably a bit easier. But for all these models, these transition rates depend on unknown parameters. And we might have an idea, sort of broad idea, about the values of some of the parameters that govern these transition rates, but in general, a lot of them are unknown, and they adhere not only to the pathogen, the disease that's spreading through the population right now, but they also adhere to the population itself, its structure, people's behavior, and they also adhere to the model that we've chosen, of course. And you know, there's a whole branch of statistics that really sort of thinks about how can we compare parameters between models with different structures. And the bottom line is you can't, or if you do, you have to be extremely careful how to do it. So parameters depend on the model, certainly depend on the pathogen of interest, and they depend on the population structure. And so what I'm really saying here is that just being able to simulate your model forward in time, given a set of parameters, is not quite enough. What we need to be able to do is to learn the parameters of our model, given various observables on a disease system. And observables tend to be things like case incidence data. So how many infections are happening per day. And we often observe that imperfectly. For example, recording of lateral flow tests. You know, stick the swab up your nose and stick it in the liquid, and then pour the liquid on the little sort of chip thing, and then watch for the red line, and then log it with UKHSA, whether it's positive or negative. So that's a noisy observation of perhaps the number of a proxy of the number of infections per day. Or we could go out into the population, as the Office for National Statistics, the ONS, and also the REACT study at Imperial College did, and actually do a randomized study where you go out and test a random number of people in different parts of the country, and then you say, well, I've tested N people and X of them are positive, therefore X over N is my best guess of prevalence. Okay, so there are lots of bits of data, noisy observations of our epidemic process, and one of the ways that we might want to think about kind of constructing an inferential procedure on our model is to kind of wire up all our model parameters into a probabilistic directed acyclic graph, a DAG. And so what I've kind of shown here, this is very hypothetical, but here in the middle we have our SVIR model, and I've drawn that in a circle because we sort of assume that we don't directly observe that process happening in nature. We observe it through some kind of, again, random observation process, which I call Y, and I've observed that it's in a square. And then above our epidemic model, we have kind of various parameters. So we might have like a baseline infection rate beta. We might have a rate at which you recover from the disease gamma. We might, if we think that the rate at which you get infected changes depending on where you are in the country, we might do things like put a spatial Gaussian process on the infection rate. So infection rates in my part of the country, up in the Yorkshire Dales, might be a bit different from infection rates in Cambridge or in London, so on and so forth. And we might want to learn what that risk surface looks like in order to be able to detect areas of the country in which the disease is spreading faster than we might otherwise expect. So if we do that, then it's a fairly well-known bit of theory that allows us to sort of transform these models by conditioning on the model outputs. And if we transform these models, then the question is, well, how do we then go about inferring what beta, gamma, mu, sigma are conditional on our observations Y? And for this, most people, I think, nowadays would turn to Bayesian inference, because Bayesian inference provides us with the machinery to actually say, well, the way that we're going to estimate beta, gamma, mu, and sigma is by considering them as probability distributions and then drawing samples from those probability distributions, drawing a histogram of those samples, and hey presto, that's your inference. And there are a whole raft of algorithms that allow us to do that. So MCMC, Markov chain Monte Carlo, is a way of drawing from probability distributions which are unnormalized to integrate to one. Sequential Monte Carlo is a way of trying to integrate out latent states, hidden states, so in this case the SVIR model. ABC, approximate Bayesian computation, and then more recently kind of emulation methods sort of come out of the uncertainty quantification world as well. And that's not an exclusive list. What I'm trying to sort of say really is that there are lots of different Monte Carlo algorithms we might want to employ for a given model. And these things are complicated to code. And actually trying out different algorithms on the same model is complicated just by the weight of coding. Wouldn't it be good if we could come up with some pre-canned samplers that we could just apply to a given model and do everything quickly? So to do this, there are lots of PPL people in the room. There are lots of non-PPL people in the room. There are some DSL people in the room as well. And you'll know that kind of achieving effective software implementations of not only the model itself, but the algorithms that work on that model needs careful thought. And really what we want to do is to arrange our code so that we end up with transparent code, code that's kind of readable, code where we can sort of see what's going on in the model in isolation from the logic of doing computations on that model. And I think that, going back to my sort of one of my early slides, I think that helps kind of scientific and public scrutiny. And I think that's something that we should definitely strive towards. Doing it better than we used to, but we're not there yet. The other thing we need to be able to do is to change our models quickly. And certainly those of us who are involved in the SPI-M, the severe, I'm going to get this wrong now, I'm going to look at Paul because he probably knows this, the Severe Pandemic Infections Modelling Operational Committee. Scientific. Yeah. Thank you. Scientific Pandemic Infections Modelling operational committee, which was a subset of, or a subcommittee that advised SAGE and sent policy advice ultimately up to the Prime Minister. We were always being asked new policy questions. Oh, what happens if we do X, Y, and Z? And we were having to adjust our models, change the model structure in real time, and recode a lot of the samplers that then train that model on data that we were receiving. So we want to be a bit more flexible than having to stay up until 3 o'clock in the morning debugging code. So maybe a bit of careful thought around how we arrange our algorithms with respect to our model will help. And then I think one of the biggest barriers we have currently is the education barrier in onboarding new researchers, early career researchers, into this kind of hot mix of epidemiology, fairly advanced computational statistics, and some fairly advanced computer science as well. And particularly for people coming in from kind of health or biological backgrounds, that's a massive learning curve. And anything we could do to lower that barrier to entry to people who know lots and lots about disease systems, but perhaps are weaker at coding, I think it's a good idea. So it's a way to enrich our subject and to pull in people who have really good understanding of the systems on which we work. Okay, so I just wanted to kind of summarize a bit of the discussion that we've been having during the MIP program over the last couple of weeks. And we sort of started off, I think, here right at the beginning of last week. I put this slide up as a sort of summary of a discussion that we'd had on PPLs. And the kind of point was made really that we've got this really good notation for writing down differential equations, you know, these kind of deterministic models. Actually, that's not really a problem. And given, you know, software like Mathematica or even, you know, the DEsolve package in R, actually implementing these things is not particularly hard. Where it gets much, much harder is for stochastic simulation setups. And, you know, given that most of us, I think, gravitate towards stochastic setups because they allow us to deal with discrete numbers of individuals. They allow us to kind of marry up spatial units where we've got very small numbers of individuals with spatial units where we've got much larger number of individuals. The notation in the mathematical literature is kind of not consistent. Implementations of these models are not particularly consistent. It's kind of the Wild West out there. And that really is a barrier, I think, to translating or communicating these kind of models. And the question I always get asked when I have new PhD students, looking at two of them at the back because they ask me this as well, is they pick up a paper that describes a stochastic model and they see a likelihood equation for that model, so a function that tells us the probability of observing the epidemic given all the parameters in the model structure. And they say, where does this equation come from? And if you think through it and do the maths, it pops out. But there's no kind of consistent way of explaining where that equation comes from. Maybe probabilistic programming can help. Ultimately, what we want to do is to kind of move away from this situation where algorithm logic is kind of mixed up with the model, and we can't see the wood for the trees, either in what the logic's doing or what the model's doing. And so we began a little bit of a literature review, and a few things kind of popped out, and this is really just kind of what popped out on the top of the list, I suppose. It's certainly not comprehensive. But we were thinking about the role of Petri nets in kind of describing how networks of people come together to facilitate that infection process. And there are a few kind of ongoing projects that are quite interesting. So the Kappa language that comes out of molecular dynamics describes Petri nets of molecules interacting, and William Waits up at Strathclyde has been using that and applying that to infectious disease settings. Great mod, which is where the picture comes from, comes out of Turin, again using kind of PetriNet setups. And Simon Frost's currently, who's with Microsoft in Seattle, but also has a post at the London School of Hygiene and Tropical Medicine, is currently exploring these things in the context of algebraic Julia. But I think there are some questions about PetriNets that kind of came out last week, particularly how they scale to large individual-based models or agent-based models. Do they really work? Are they, PetriNets have been around for a long time and the subject hasn't adopted them yet. So I guess the question is why? Then there are a few kind of compositional frameworks around. I forgot to change the picture, so I haven't got a picture of the Kendrick disease modeling language, but people are thinking in this kind of compositional way of how can we express models using small building blocks that fit together to form much more complicated structures in a way that the resultant model is kind of correct by construction. And I think function programming is useful here. We'll hear about that a little bit later today. And sort of decomposing how epidemics work in terms of kind of applying functions to a state and modifying that state, and then how those kind of state transformers then compose together. And then lastly, Cambridge is arguably the home of probabilistic programming. Wimbug software came out a long time ago now. And we got some very illustrious people in the audience who facilitated that. And since then, there's been a sort of an explosion of PPLs. And here are just a few that are kind of commonly used in statistics, I suppose, from my subject. But I mean, there are lots more. There's quite a comprehensive Wikipedia page on PPLs, and it's got sort of 30 or 40 languages listed there. There's no doubt that PPLs save time, particularly for kind of standard modeling problems. But I don't think they quite pushed out effectively into infectious disease modeling quite yet. And I think that's what we really want to ask the question today. It's kind of, can we bring ideas in domain-specific languages for things like agent-based models together with concepts in probabilistic programming so that we can kind of get the best of both worlds. Just a plug for something that we've been working on at Lancaster in collaboration with our friends at Glasgow. This is the GEM project, which really was kind of asking the question, could we take something that looks a little bit like the bugs language, and could we extend it to provide definitions of state transition models? And this is probably about 5 or 6 years old now. We've really been focusing on the back end and actually asking ourselves, well, lots of the probabilistic programming literature has exploded in the last kind of 10 years with the advent of something called the Hamiltonian Monte Carlo algorithm. Lots of those frameworks don't really think about, think about how we can compose models, that's great, but they don't really think about how we can compose MCMC, SMC, ABC samplers together in a way that's kind of easy and quick for the user. So we've been thinking quite a lot about how we could do that and how we could do this in Python, particularly using kind of TensorFlow and JAX so that we can get the best of autodiff libraries, but also performance sort of transparently. If you just happen to have a GPU sat on your machine, the library will use it transparently. So lastly then, my last 30 seconds, I just wanted to leave you with some questions to try and just sort of motivate the day, really. So I've already asked the first one, can we unite DSLs that are out there for describing the systems of interacting agents with concepts in probabilistic programming? Are we really already there, or are there components that are missing? Have we got the right level of abstraction in the languages currently? assuming that we do, or assuming that we can create a good abstraction, is that abstraction going to be performant? It's no good having a probabilistic programming language that's very beautiful, but without the optimizations under the hood that then actually make the samplers run quickly and efficiently on available hardware. One that Simon Frost asked yesterday is, why are there so many PPLs out there? Why have we not gravitated towards a kind of a consensus on this? Maybe it's ergonomicity. Maybe people coming from different disciplines want to use probabilistic programming languages in different ways. And maybe the look of a language, the ergonomic feel, really ultimately affects whether or not it's adopted into a particular subject. Also, this sort of question, why is there so little work on composing Monte Carlo samplers? Lots of work on composing models, less work on composing samplers. Could we actually push this back a bit? And then finally, a question really for the modelers and maybe a challenge for the computer scientists that work in this area for the modelers is, how do DSLs actually allow us to do what we do better? So how can they actually fit into our subject to increase our productivity, increase the transparency of our science, and ultimately the trust both internally within the scientific community, but also in terms of policy and public trust. Okay, so sky's the limit. Hopefully we can get some good discussions going today. Hopefully we can get to know one another over coffee, over lunch. And actually, if there are areas of commonality in what we do that appear promising in terms of helping us resolve this infectious disease problem better, then let's pursue it.